Hello, class. Inside of this video, I want us to do a very quick introduction to our Chapter 5 content. So, with regard to that, Chapter 5 is going to be based on sections 5.1, 5.2, and 5.3 on how probability quantifies randomness. So, a couple of definitions for that, yes. Random phenomena are situations for which the outcome is uncertain. A small number of observations is where the outcomes could look different than their expectation, while a large number of observations increasingly approaches their expectation. That has a fancy sounding name attached to it called the law of large numbers, which we'll be talking more about in the future. Law of large numbers. There we go. So the probability is the long-run quantification of uncertainty. Phenomena is any observable occurrence. And in order for us to have what we're doing on some of these, sometimes we have something known as an independent trial. That's where the outcome of any trial is not affected by the outcome of any other trial. Currently, that's not going to be too much of an issue, but definitely down the line with what we're doing, could be something that's kind of important to know. Long-run behavior of random outcomes. Again, this is that law of large numbers thing. Rolling a six-sided die 100 times and counting the number of sixes can vary each time, right? If you do it once, you'll get, one occurrence of that. But if you start doing it, a couple of times, a small number of times, it's not going to necessarily be the expectation, which in this case, a value of 1/6. It'll jump all over the place. But the long run occurrence tends to be predictable, approaching that value of 1/6. So Jacob Bernoulli in 1689 defined this as the number of trials increases, the proportion of occurrences of any given outcome approaches a particular number in the long run. Again, called the law of large numbers or law of averages. You could kind of see it in this picture here. Just make that bigger, where it shows that the proportion of that rolling a six-sided die to get one of those six sides. At first, when it was a small number, it was, jumping all over the place. But as we increase this without bound up to 10,000 trials for this, it's approaching that value of 1/6. So it kind of guarantees that long run performance that we're looking for. So random phenomena. In order for something to be truthfully random, they need to have equally likely outcomes. That's where every outcome has the same chance of occurring. And the total of those probabilities would be 1. So, like, for example, with rolling that six-sided die, the probability of getting a 1 is 1/6. Rolling a 2 is 1/6. Rolling a 3 is 1/6. Rolling a 4 is 1/6, which was a bad spot to rate this. Rolling a 5 is 1/6. And rolling a 6 is 1/6. All of them have that same chance of occurring, so they're equally likely. And if you were to add up all these probabilities, you get a nice value, 1. In theory, though, we can observe the number of occurrences as the probability, called the empirical probability, but the sample proportion only estimates the probability. So only for a large number of trials is this close to a classical form of probability, which is the expectation. And these empirical probabilities use something called relative frequency, the probability of an outcome, as a short-term proportion, which may not, and usually does not, equal what we expect, which is fine. This is not really shown or defined here as something that should be happening, but let's face it, out and about in the real world, sometimes it's not always nice and easy just to, compute a whole bunch of probabilities. So we have these subjective probabilities. This is the probability of an outcome is assessed by objective information, not based on a long run of trials and not based on an experiment. There's a branch of statistics that does use subjective probability called Bayesian statistics, coined by Thomas Bayes, a British clergyman. A branch of statistics that uses subjective probability, and it uses a probability rule. The point of that one, though, is it uses a concept that we'll be talking about later in chapter 5, based upon what's called a conditional probability. But we're not going to do much involving that. I have this quote from Ben Franklin to give an idea of a subjective probability. Nothing in life is certain but death and taxes, right? No actual experiment was done to actually identify if those are certain or not. But due to the time period of that time, that's why that quote was stated, and it is indeed subjective. So, these probabilities can be thought of as sets, which is why we have these two set sounding items here. A sample space, S, is a set or collection of all possible outcomes for a random phenomenon. The number of outcomes with the repeated trials is n to the p power, p being the number of trials, and n is the number of choices. An event E is a subset of the sample space, a particular outcome or group of outcomes. So, like, for example, rolling that six-sided die, sample space would be the numbers 1 through 6. And we could define E in whatever way we so happen to want to. I'm going to call E, event E here, rolling an even number. What does that mean in terms of a six-sided die? Those are the 2, 4, and 6. Due to that. As you can see, it's kind of considered a subset, meaning that it's a smaller grouping than the sample space. So when we have these equally likely outcomes and whatnot, you start forming what's called a probability model. Each probability of each outcome must be between 0 and 1 inclusive. And the total of all the probabilities in this experiment or in this model needs to add to 1. So like that last example of rolling a six-sided die, all those probabilities were 1/6. If you add them all together, you get 1. And 1/6 is definitely between 0 and 1. So that would be an example of a probability model. For example. And as a quick another example, I have this here. We want to see if this is a probability model, given these different colors and probabilities. So red having a probability of 0.3, green negative 0.2, blue 0.2, brown 0.3, yellow 0.3, and orange 0.1. But we have a problem here, yes? This green has a probability of negative 0.2. That's less than 0. So this will be a no. This is not a probability model due to the fact that probability of green is less than 0. But if you were to, add all of these together, they actually do indeed add up to be 1. But just because of the fact there's a negative probability in here, it is still a no. So let me know if you have any questions or concerns. Thank you.